Welcome to Curious Campus, where we talk to professors from various departments at the University of Toronto about a recent research topic they've dived into, breaking down these new developments for everyone to understand. Stay tuned, you'll definitely learn something new. I'm Chubby, and today I'm here with Professor Steve, and we're here to talk about his research in his book, Computing the Climate. Steve Easterbrook is the director of the School of the Environment at the University of Toronto, where he teaches courses on environmental decision-making, systems thinking, and climate literacy. He received a PhD in computing from Imperial College London in 1991. In the 1990s, he served as lead scientist at NASA's Katherine Independent Verification and Validation Facility in West Virginia, where he worked on software verifications for the Space Shuttle and the International Space Station. He has been a consultant for the European and Canadian space agencies and a visiting scientist at many climate research labs in the United States and Europe. Today, we're here to talk about his book, Computing the Climate. And with further ado, Steve, welcome to Curious Campus.
Hi, delighted to be here.
Really excited for this conversation we're going to have. So, to get us talking about this, as was mentioned in your introduction, you have come from a computer science background, having done your PhD in that and such. So how did you find yourself working on environment issues?
So I'm celebrating my 25th anniversary at U of T this year. So 25 years at U of T. I came here after working for a while with NASA on big problems with control systems for spacecraft. And I started out doing some work here with some big software companies, IBM, Microsoft, and so on. But I also came to Toronto, my kids were born, and I'm thinking about their future. And I've always been an environmentalist, but my research and my environmentalism were always very separate. And they kind of came together thinking about where I want to go next in my career after I came to Toronto. And it took me a while to figure out kind of how to find a research project that married the two together. And the way it came about was I'm reading in the newspaper and everything about climate change and thinking this is a massive problem. It's going to affect all of our futures. This sounds like a challenging problem that I'd like to work on. And the question is, well, where's there a role for a computer scientist in that space? So I got chatting with one of the professors in physics. Actually, I talk about him a little bit in the book, Dick Peltier, who is probably our most senior climate scientist at U of T. And the story's in the book. We met for a beer in the faculty club and we just got talking, what do the scientists do? Where's there a role for me? And he described these models that climate scientists build. So they are massive, complex simulations of the Earth system, of the atmosphere, oceans, and so on. And he says, as pieces of software, they're actually not very good. Scientifically, he says they're really good. As software that's easy to use, easy to work with, there's a lot to be desired there. So I said, okay, well, that's the kind of problem I know how to solve. I know how to build complex pieces of software. I understand how teams work. I understand how to make software usable. Here's a challenge for me. So then I asked him, basically, how do I get started? And the question I had for him really was, who's doing this well? Because when you're moving into a new field like this, I didn't want to reinvent the wheel. So I didn't want to go and visit some labs and propose some things that other people have already solved. So I said, well, let's find a place to start with somebody that's already doing the modeling really well. And then I can go and see how other labs compare to that. So he suggested I go first of all to the UK Met Office, which is the big meteorological office in Exeter. So what I did was I set up to spend an entire summer there. I spent 3 months in England, hanging out at the Met Office, kind of wandering around with my notebook in hand, watching what the modelers do, watching how they work with the software, watching the data that they feed into the model, the data that get out of the model, sitting in on their meetings. Yeah,
that's really cool. And I guess you just learned a lot and it produced this book. That was really informative.
It took a long time to get to the book. So I first went into this thinking very much in the traditional mode of academic research. I'll write some papers, publish them in journals, publish them at conferences, kind of studying these software practices of these modelers. But the more I got drawn into this community, working alongside these scientists, and it's so fascinating, this was nearly 20 years ago. I've been working on this ever since. It just drew me in. But I realized there's a gap that nobody outside these labs really knows anything at all about the models. So I realized rather than writing more academic papers, probably what I should do is write a book and make it accessible. So that's I think it took me 5 years just to figure out how to put together a book? Like, how would I structure it? What would the chapters be? How would I tell the story? So yeah, it took a long time to get the book together.
We can see from the dates in the books as well, where you talk about your initial discussion in like the early 2000s and up to here. So yeah, really, really cool. And I guess like you probably also could tell like no one else really knew about the Met and what they were doing because you were based in the UK, right? Prior.
The UK Met Office has an interesting mixed reputation in the UK. It is one of the best weather forecasting organizations in the world, and they provide weather forecasting for about half the globe. Like there's a huge number of commercial organizations rely on their weather forecasts, and they have this reputation as being one of the best. But also they're well known in the UK in papers for the few occasions when they get it wrong. The newspapers tear them apart. You know, why are we spending all this money on this Met Office? They failed to predict this storm. It's like, okay, they got it wrong once. Anyway, yes, so it's kind of this mixed. Yeah, so I knew about the Met Office, both parts of that reputation before I went there. Yeah.
Great. So yeah, that is like really cool to like hear about your experience with the office like prior to even like going into the research. So talking about the book then, you began the book by introducing the question posed by former US President Jimmy Carter about how certain can we be about projections of future climate change from computer models? And this question was then passed on, and then from the National Academy of Sciences, Joel Carney came along and broke down the question further into how fast will emissions rise? How will climate system respond? And how will this affect us? So based on everything that you've learned in like the past 20-ish years, did you find this to be kind of cover all of the topics that were needed to diagnose this?
Kind of. It's an interesting way of breaking down the question. And even the fact that question was being asked. So this is Jimmy Carter's administration in the 1970s asking scientists not, you know, what is this thing called climate change? Is it real or anything like that? It's, okay, we're convinced it's real. How bad is it going to be? And what do we need to do to prepare? It was like a very serious question saying the science seems to be telling us this is coming. So the question the White House was asking back then is really how sure we can be about the numbers. I find that just that historical moment really interesting. That's kind of why I started the book with it. Like back then, 1970s, lead politicians, the president is asking these questions of scientists. So yeah, and so Joel Carney is an interesting character. He's kind of sometimes described as the grandfather of numerical weather forecasting because he led the work in the 1950s and 60s to build the first computerized weather forecasting systems, which is kind of the birth of how modern weather forecasting is done. And so they called on him to lead this scientific group as part of the National Academies. What's interesting is they spent a week out at a retreat, Cape Cod. So they broke the question down. And the reason they asked those three parts is because I think this is a really good way of thinking about how we understand what we can know versus what we can't know, and where we have to do some guesswork versus where we can provide really good, solid answers to the questions that, you know, political leaders are asking. So one part of the question is, how will human activities result in changing greenhouse gas emissions over the future? And that's not a question that scientists can answer. It's really a question for economists, technologists, even politicians, because it depends on how quickly we're going to switch to alternative fuels. It depends on how fast our economies are going to grow. It depends on things like international trade, where those things have a big footprint in terms of greenhouse gas emissions. So what the scientists do is they say, okay, well, there's so many unknowns in that question. What we can do is we can create a number of scenarios and say, okay, here's a scenario where the world switches very quickly to clean energy, fossil fuel use declines, maybe international trade grows or it declines. So we can have a number of different scenarios. And we work out under each of those scenarios what would future emissions year by year look like. Then you can feed that to a computer model to ask it, well, what does the climate do in response? And that was the bit that Carney's group focused on. They said, this is the bit where we can provide some very clear answers. That if emissions grow in the following way, here's what we can expect the climate system to do over the next few decades in response. So that's what their models focus on. It's a kind of if-then. If change emissions in some particular way, how does the climate system change? And then the third part is, well, how does that affect us? And we talk a lot in climate science about temperature rises of, 2 degrees centigrade over some period of time. Maybe we look at the end of the century and say maybe we'll get to 3 or 4 degrees by the end of the century. But that means nothing to nearly all of us, right? And it sounds like a small rise in temperature. So the question then of how that is felt by people, by ecosystems, how it affects our communities is a much harder question to answer. And, since Chinese time, the research on that part of the problem has grown dramatically. So we've got a much better understanding of what those climate impacts will be. But also there's still a lot more uncertainty. So the middle question is where there's most certainty. We can say, if you do the following thing with greenhouse gases, we can be fairly confident about how it will affect global temperatures. But the before and after questions is where all the uncertainty lives.
So based on that level of understanding that you achieved through this research, why did you then decide to focus on the physics models, which were based on seeing what happens when we do all these changes to the environment rather than the economic models, into seeing what are the effects of all of this?
Good question. And I think probably several different answers to that. There's probably the answer that I think I had at the time that led me down that route. And then there's me looking backwards and from now and saying, did that make sense? Why did I choose that? And perhaps looking back, it's almost like I fell into it, from that initial conversation I had with Dick and going to visit the Met Office. Those physics models they dominate the field of climate science. That's where a huge amount of effort is put. That's where there's a huge number of scientists engaged. And I count thousands of scientists around the world working on those models in various aspects. And so it's big. It's the elephant in the room. It's the thing that's obvious to go and look at when you first start looking at climate science. Compared to, say, the economics models, climate impacts models, the things that affect those other two questions. Certainly back when I started this, there was work going on in it, but it was very diffuse. It was kind of one or two scientists, often in universities, working on it in their own way without a big coordinated effort. That, of course, has changed over the time that I've been doing this. There's a lot more coordinated work on that now. But it was harder to get hold of. So in some sense, it was easier for me to go in and study the big models because they're big. And when you get to something you do that scale, it's kind of fairly obvious what's happening. But also maybe one other answer to that. I'm glad that's what I focused on, because I think for me, working my way into this field, because before I started this work, I really didn't understand how climate science was done. I think it gives me a good basis now to look at the other questions now that I've mastered that middle piece, those physical models. So I think it was the right place for me to start.
Do you think you would ever switch and look at the other questions then?
Yeah, well, I've been thinking about, and a number of people ask me, well, now this book's out, what book are you going to work on next? And I think, well, the obvious next book is the economics models. And maybe I should. I think that story needs to be told as well. And again, just like when I wrote this book, my feeling was there's no really good book out there that explains how the physical climate models are built. There's no good book out there that really tells us how the economics models are built and how all of that research comes together. And what worries me is that it's still a lot more immature than the physics work. And so the book might be harder to write, but it needs writing. So, I think that's the obvious next project for me.
Yeah, that sounds really cool. So talking again about meteorology and how it's come to what it is right now, you've talked about that by the end of the 1800s, there were 3 distinct traditions within it, including the empirical, which was the collection of weather data, the theoretical, explaining the properties of the atmosphere using the laws of physics, and the prognostic, which was the forecasting. So what did you learn really about this unification, and did you even process how this was possible?
Yeah, it's an interesting question, because what brought those 3 traditions together really was the birth of digital computers. And so this is where I look at this field and say, well, this is me. This is what I know about. I know about digital computers. I know about their history. I know about that work, especially during the Second World War, where there was suddenly this invention of electronic computing and people asking questions about, hey, we've built these new tools. What can we do with them? It required these new tools to unify the work. I mean, I touch on this point quite a lot throughout the book, that the models become a place where people who perhaps hadn't worked before work together before can come together and collaborate. You can put something into a model, then you can show somebody else, this is what I'm working on, here's how it works. And the model makes it real. The model, you can show them what's happening rather than just talk about abstract theories. I feel it allows people to collaborate in new ways. It opens up those kinds of conversations perhaps in ways that were hard to do before. So those three traditions still exist, but now they're woven together in the modeling. So, in order to build a computer model, you need the theory, you need the key equations, and those come from the theory. You need the data, so you need somebody to go out and do that empirical work, collect the data to feed into the models. And so this is the key test of a model. How good is it at predicting the future? So you run it for a little bit and then you wait and see what happens. And this is how you improve your model. You get better and better at running forecasts. So you need the forecasting piece as well. So to build a good model, you need all of those things. But without the computers to run it on, those scientists aren't going to get together and collaborate.
It's really cool that you touched upon computers because, as the title says about computing the climate, computers were a big part of what you found in the research of this book and even in all the content. So I found it quite interesting because it seems more like a few decades ago that researchers were heavily relying on these computers, where it was not really a thing recently prior to then. Did they soon become dependent on this?
I try and get this across in the book as well, that the story of progress on these models and to some extent climate science more broadly depended upon progress in the computing platforms they had available. It would not have been possible if we hadn't had... I talk a little bit in the book about Moore's Law, which for people that don't know it, this is the fact that we can just get faster and faster machines every year. Every year, the computing industry brings out a faster machine, and every couple of years you think, my machine's too slow, I can buy a faster one, and it runs much faster. And the climate scientists are doing the same thing. They run their models on supercomputers. These are typically some of the fastest machines in the world because what they're doing, these simulations of the whole planet, are so computationally demanding. They need the very best machines. And then every few years they replace their supercomputers because there's another one that's come along that's 10 times faster, and they can improve their models just by running it on a faster machine. So there's this really tight coupling between development and growth of what you can do with computers and how fast they can run and what the scientists want to do with their models. It's you can't have one without the other. They both matter. So I had fun kind of weaving those two stories together because I think they are deeply woven.
I find that really fascinating. So I read a lot of books on the side as well, and it's reading a lot of things about how we got to our modern computers and stuff. Everyone brings up Moore's Law. And now I wanted to ask you if you know, because Moore's Law just says that our ability to do computation will just double every few years. But it seems that people are trying to make sure it's true rather than seeing whether it's actually possible.
I read a lot about Moore's Law when I was doing the work for the book because one of my physicist friends likes to joke that we call it a law, but in terms of physics laws, it's not a law. It's just an observation. So there's nothing that guarantees that it's true, unlike the laws of physics, where you can't violate the laws of physics. You can violate Moore's Law. It's an observation that just happens to have held true. But then there's this feedback loop because, through the 1960s and 70s, when Moore's Law was first talked about and written about with this kind of doubling in speed every 18 months, the computing industry latched onto this and started to gear all of their research and development to keeping it going. So the fact that we identified Moore's Law and talked about it became this feedback loop that the computing industry depended upon it because that's now how you sell computers. You tell people you can buy a faster machine than you could when you bought the current machine. And if you can't do that, you're probably not going to sell them a new computer. So Moore's Law has taken on a life of its own and become this thing that the entire computing industry bases its business model around and bases its research and development around. And there's a whole series of papers going all the way back to at least the 1990s predicting the end of Moore's Law. So there's loads of them just saying Moore's Law is going to end by the end of this decade. And of course it didn't end. It still sort of holds true today. But what's happened is the computing industry has got more and more inventive about how to build faster machines. Originally, Moore's Law was driven just by miniaturization, by packing more circuits onto a chip closer together. You're limited by the speed at which the electric signals can travel. Pack them in closer together, signals don't have so far to go, they can move faster, you get faster computing. So just miniaturization year after year after year gave us faster computers. And then they started to reach the limits of miniaturization. You get down to the physical level where you're so close, you're talking individual electrons, and they're, not much further apart than the size of fundamental particles. You can't miniaturize beyond that. So what did the computing industry do? They said, Moore's law matters to us. We've got to find another way to keep the speed up. So they started offering us parallel machines. So now you buy, we started out with dual processors in our laptops and then quad processors. And they just said, well, we'll just put more chips in rather than miniaturizing the existing chips. So they found a way round. And that's been the story since then. Like every time they discover a limit of one way of pushing Moore's law further, they find another way, another inventive way to get there. It's fascinating. Yeah.
I do think that's quite fascinating. Great. So coming back to Jimmy Carter's question, you talk a lot about how there's a difference between what research scientists are looking to do and what everyone else really wants to know, which is what is the weather next or the climate in a few years going to be compared to what research scientists want to know about actually just understanding the climate system. So I'm very curious, what really is the difference in these two? Because the outcome would be the same as you have the model, it predicts something, and then you wait and see if it actually is right.
So there's different ways of explaining this. And one of the ways I like to think about it is a weather prediction. You want specifics. You want to know, do I need to take my umbrella tomorrow? Those kinds of questions. Will it rain or will it not rain? How cold is it going to get next week? So these are very specific questions based on where you are in the world, like at my location, where I am, in my town. What will the weather do next week, tomorrow, whenever it is? Whereas climate, one way of thinking about what climate is climate is the typical weather patterns. So it's not will it rain next week, but on average, does it rain on the second week in December in Toronto? Climate questions are much longer term questions. You want to work out what long-term averages and extremes look like. So you can use the same model to answer both questions, but you run it in a different way. So with a weather forecast model, you feed in the model with all the current conditions. Like in the last 24 hours, what happened? And you start the model off with that data and you run it forward in time to say, well, how will those weather patterns we've observed in the last 24 hours unfold over the next few days? But the longer you push it, the more the errors mount up. So by the time you get to about 2 weeks out, there's so many errors now in the model in predicting how weather systems are going to play out that it's hard to give an accurate forecast. But if you keep running the model for months of simulation and then you look at the long-term averages, that tells you something about the climate. So it's the same model, but it's a different way of thinking about it and using it to answer those two different questions. But that means we can't tell people 6 months' time, what's the weather going to be in your community on a particular day.
It's cool. I've heard that for weather prediction, that looking at historical data for that same day over past years is more reliable than looking at data from the days before to model it. Is there any truth?
Kind of, and that's how they used to do weather forecasting before the computers came along. So in the olden days, before we had digital computing, they would have all of these weather charts all printed out on paper, all indexed in interesting ways. And they'd look at the current conditions and they'd say, what's the closest we've seen in the past to what it looks like now? And they'd go back and they'd look up those weather records and they'd say, okay, well, when this weather pattern happened 20 years ago, here's how it played out. So that's our forecast. And that actually gets you a long way. If you can find a similar weather pattern, it's likely to unfold in a similar way, at least initially, and then kind of things diverge a little bit, so it gets more and more inaccurate. So it's not bad. On the other hand, with what we do with modern computer forecasting, they're much more accurate than almost anything else. And that's largely because the data gathering for the current conditions is so rich. There is so much data collected about exactly what's happened over the past 24 hours, 48 hours, and so on, that we know fairly reliably, wind speeds, temperatures, all of the things that affect how weather patterns play out. We've got this massive observing system that observes planet Earth, and so we know what's happening. And so kind of using the model to play that forward in time now gives you a much better forecast than going back and looking at past conditions. But there's one interesting thing that's happened in the last 2 years, and I don't talk about this in the book because I'd pretty much finished the book before this unfolded, is people are now using machine learning techniques to go back to the old ways to train a machine learning algorithm on all these patterns from the past. And actually, if you combine that with the modeling, you do better than either. So you put both techniques together using modern machine learning techniques, and some of those new forecasting tools that they're building in that approach are looking really promising, particularly, and here's where I think it gets interesting, particularly to extend the range of the forecast. So go beyond predicting the weather for next week. If you want to know in a month's time, or you want to know, like farmers want to know when a growing season's going to start, those kinds of questions. You want more than a week. Or you want to know when the next big heat wave or drought is going to hit. And you need more than a week for those kinds of things, for planning, for example. That's where I think putting both kinds of forecasting together is really going to help us improve things.
Very exciting, right, for the future of climate research. Based on that, then, do you think that all of these questions from the general public about weather forecasting has it all impacted, could be possible within climate research? Because this was maybe not really a thing that climate scientists were thinking about or worried about.
There's certainly a gap between questions that people want to know and the scientific community and what they work on. Something we've started working on in the last couple of years, particularly not so much with respect to weather forecasting, but with respect to climate change, like what to expect. So the models tell us all of these things about averages and extremes and overall patterns and how those patterns will shift. That's not what people want to know about climate change. They want to know, how will this affect my home? How will this affect food prices? How will this affect my ability to go about my work? Like, where should I live? Should I buy that nice seaside coastal property, or is that going to fall into the sea? Those kinds of questions. How's it going to affect my insurance? What has typically happened in this field is we've used the computer models to create all of these big forecasts for how the climate is going to change. And then we've taken that data and processed it in various ways to get closer and closer to what we think people care about when they're worrying about climate change. And been in a number of workshops in the last couple of years where people have said, this is backwards. We should start with the questions that people really care about and work from those to say, what data do we have available to answer them? Otherwise, we're going to miss things that are important to people. There's going to be questions that we're just not answering because we started with what we can do in the models rather than what really matters to communities who are impacted the most by climate change. And it particularly matters for folks around the world, particularly I'm thinking in the global south or in poorer communities where they have the least resources to cope with climate change. They're going to see the biggest impacts. We know they're going to have the biggest impacts. But if we're not listening to them and not listening to what they're experiencing, and we're just saying, well, this is what the models tell us, and so go away and use this knowledge, then we're not serving those communities very well. So I think there's got to be a change in the way the research works that listens much more to communities, brings them into the research process and says things like, just help us figure out even what research questions we should be trying to answer based on what are you experiencing, what are you worrying about, what impacts are you seeing in your own communities. And making sure that we bring everybody's voices into this, that we're not just looking at, the wealthy people in the suburbs. We're looking at everybody, no matter where they are and what they're experiencing. So it's an opportunity for us to be a lot more diverse in who we're listening to, as well as rethinking how do we choose which questions to work on.
You have talked about how you've visited a lot of climate labs in Europe and the US, and based on what you said, do you think there is more involvement from perhaps climate labs in the global south and other places?
Well, there's certainly interest and a lot of goodwill. So the modelling centres I visited, they're all in rich countries. They're in Europe, they're in North America. Much of the history of climate modelling is in wealthy countries that can afford really big research labs, can afford those supercomputers to run them on. But things are changing, and I've seen, in the last few years, a lot more working alongside research centres in the global south, getting the research located there, building up their capacity. Sometimes that means we're taking models that were developed elsewhere and localizing them so that people can then work on them themselves in those communities. But it's a shift in how the work has been done. So either, what do? Do you bring people from, let's say from different parts of Africa, bring them into these climate modelling centres in the global north, train them up and send them back home again? Or do we send scientists from elsewhere to go and work in and kind of build these new research centres kind of close to where the action is? The answer is probably a bit of both. But a lot of it boils down to capacity building. How do we build capacity in those countries for them to do this research themselves rather than relying on somebody on the other side of the world who doesn't understand the local context?
Yeah, it's just to see how education like transforms us and gets people to where they need to be. And back to talking about predicting the weather then, you talked a lot about chaos theory. So I'm very curious about what you say is like the significance of this to climate forecasting and in it not being able to allow us to predict the weather.
First chapter plan for my book didn't have chaos theory in it at all. And the more I looked into it, the more I realized, you know what? I need a whole chapter on chaos theory. I need to explain this because it's a bit of a mystery to most people, I think. And probably people know about the butterfly effect. I thought, okay, I can start there. But maybe people don't know a lot more than just that kind of gut level idea. You know, a tiny change, the butterfly flapping its wings seems to cause some massive change elsewhere. Okay, how does that work? But I realized that chaos theory is absolutely central to the story of our understanding of climate change. So as I said, it grew to be a whole chapter in the book. And I wanted to explain it in a way that people would come away with this good intuition. Like, what's chaos theory all about? And it comes back to what we were talking about earlier about, feeding in all that data to a weather forecasting model to say, here's how conditions are right now. And then the model calculates forward in time. And typically what a weather model does is it calculates 1 hour time steps. So it says, here's current conditions right now. Now I'm going to calculate 1 hour into the future. Here's how those will change. And then having done that, we go another hour and we just step by step through into the future. And what happens is that tiny changes in the initial data that you give the model grow over time as you go time step by time step. So this is like the butterfly flapping its wing. It might be changes in one number, let's say a number for wind speed, and it might be changes right down in the decimal places in that number, which at first, over the first few time steps, you can't see any difference. It's like no difference. And then at some point, the weather patterns start to diverge because what's happened is that tiny difference has grown. As each time step, it grows and it grows and it grows. And at some point, you see the weather doing something very different. If you run the model for two different conditions that vary by that tiny amount, several days into the future, you will see completely different weather patterns emerge. And this is what some of the early climate models, weather modelers discovered. They ran their classic example is Ed Lorenz, who was sometimes described as the father of chaos theory, was running a weather model and something went wrong and there was another output he wanted from the model. So he repeated the run from one of the points where he'd saved the data, and it ran for a while looking the same as the first run he'd done, and then it diverged. And he thought there was something wrong with his computer, like something had gone wrong. I ran the same program with the same inputs and I should have got the same results and I didn't. And so that led him to this whole series of insights about this idea of chaos theories. So the other way of thinking about chaos theory, technical term, is its sensitivity to initial conditions. That a very small change in the initial conditions for a chaotic system grows over time to the point where suddenly you see very different behaviors. But it takes time for those differences to emerge. So, yeah. And then this is the difference between weather and climate, because for a weather system, if you keep your forecast within a small range where you can't see those differences growing, you'll get accurate weather forecasts. If you push it beyond that, chaos theory will get in the way and all you'll have is a forecast that's not going to happen because it's completely different from how the real weather system's going to work. For climate change, that doesn't matter because as long as you do, and this is what the modelers typically do these days, you do lots and lots of different runs with lots of very small changes in the initial conditions, you're interested in averages. So if I run the model 100 times and change the initial conditions a little bit each time, I can capture the range of things that can happen, and then I can talk about average temperature, average number of storms, what are the hottest days, what are the coldest days in that range of runs. And so chaos theory it kind of matters because you've got to accurately capture how a chaotic system works, but it doesn't get in the way of predicting climate change because you just run the model many times over and look at averages.
That is like a really cool concept. I felt like that chapter was pretty eye-opening to me, like compared to like everything else to quite really grasp.
it was eye-opening for me. I knew a little bit about chaos theory before I started the research for this book, but boy, did I learn a lot just putting that chapter together.
So you talk about different climate modeling, looking at temperatures on land, temperatures in the atmosphere, and temperatures in the ocean. So when you eventually talk about ocean modeling, it does make it seem like it would be easier than looking at the atmosphere, because body of water, it seems like there are fewer factors to consider. But it turns out that's actually more difficult. Could you talk about that?
One of the problems there is we really don't know what's going on in the ocean. It's like, we talk about exploring outer space. We really have not explored the deep ocean anywhere near enough. So one of the challenges is just a lack of data. It's really easy to observe the atmosphere. We've got all sorts of ways of doing it. We've got ground monitoring stations all over the world that just watch the sky, kind of sense what's happening. We can send up balloons, we can put sensors on aircraft and so on. And you can kind of build up this three-dimensional picture of what's going on in the atmosphere. It's a really good data collection. In the ocean, we know what's going on at the surface because we can put sensors on ships and buoys and collect data about the surface of the ocean. But going down deep, we really have very little data about what's happening. So that data collection lagged several decades behind our knowledge of the atmosphere. So atmosphere modeling got going a lot faster. There's a difference in scale as well, but then there's the other complexities for ocean modeling. For example, the shape of the seafloor matters a lot. You've kind of got the ocean getting shallower towards the coast, although the profile of that shoreline changes dramatically from one part of the coast to another. And so ocean currents will do different things depending on the shape of the shoreline and the depth of the waters around the shore. And if you don't get all that accurate, you're not going to get ocean currents correct. And then there's one other thing that I learned about studying ocean models. There's this worldwide pattern is known as the sometimes called the Great Ocean Conveyor. Scientists will call it the overturning circulation. But it's this connected set of currents that go all the way around the world. It's warm waters in the Atlantic and Pacific Ocean moving northwards towards the poles. Then as they get colder and saltier around where the ice forms, sinking, dropping down to the deep ocean and flowing back down towards the equator again. And this one pattern of currents connecting all of the oceans to the world, and it's slow moving. It takes about thousands of years for water to go the entire circuit around the planet, but it does. And I think, okay, so I've got to run a model for 1,000-year simulation to see if I'm getting these currents accurate. That's a big ask. Even with our fast supercomputers, that's still very hard to do. So you have to run the models for much longer periods of time to test whether they're getting it right. And even when you do, we're hampered by not having data from the deep ocean to say what's really going on.
Yeah, I think that's still fascinating. With a lot of people are getting more interested in bodies of water, but it's still scary because there are also tons of organisms in there that we don't quite know about.
And discoveries, we keep discovering things on the bottom of the ocean that we never, the new life forms, for example, the bottom of the ocean. We didn't know they were there.
So I want to get back to your experience of coming into this research, having not quite studied it formally and then coming into it. So you talk about how Wilhelm Bjerknes argued that accurate weather forecasting would be possible if two conditions were met: sufficiently accurate knowledge of the state of the atmosphere at the initial time, and a sufficiently accurate knowledge of the laws according to which one state of the atmosphere developed from the other. So Bjerknes also wasn't quite in meteorology at first. Based on this, and also with your experience, do you find that research experience in one field is able to break down problems in another so succinctly? Or is there a long period of learning that actually gets you to this point?
And this really captures a lot of the research that I've done over my career. I've moved around between fields, and I find that fascinating. It keeps the research exciting. There's something fascinating about moving into another field where you don't have all the background and you've kind of got to learn it as you go along. Sometimes you'll see problems in a different way from people that have been in that field for a long time. And that's valuable. And of course, sometimes you'll go in and think that some problem they're talking about sounds really simple and I know how to solve it. Now, why don't you just do it like this? And they're going to say, come on. So you also have to be very humble about it. You have to listen carefully and you have to take the time to understand what they're doing and why they're doing it before you march in and say, well, that looks really easy. Why don't you just do it like this? Sometimes those new perspectives are valuable. Sometimes they're not. But to my mind, one of the real values of people that do this is they're often better than at explaining what that field's doing because they're new to it. They're not deeply embedded in it. So if I had this conversation with a few of the climate modelers when I talked about writing this book, they said, you know what? I'm probably the right person to write this book because I'm fairly new to the field and I can remember what it's like not to know any of this stuff. And so I'm kind of writing for myself. Here's something I've recently discovered. So I can explain it in a way that makes sense to me being new to it. Once you're deeply embedded in the field, you've studied it through undergrad, you've studied it through graduate school, you're a professor now, you're so deeply embedded in the field, you've forgotten what you didn't know way back when. And so I think it is harder to describe it to outsiders when you are that deeply embedded in a research field. So to my mind, that's a really valuable thing. People moving into a new field, kind of discovering it for new and trying to describe it in their own words is a really valuable thing.
Of course, it was like a wonderful story to hear about. And I guess like very inspiring for people who do want to like look into a new research field or any new area to like learn about. And what would you say was like the most surprising thing that you learned through all of this that's like really stuck with you?
There are so many different things. I mean, there's the frightening stuff about climate change, and we haven't really talked about the really scary stuff that's coming at us in our future. Things that I think very few people understand about climate change, but, you know, having spent all this time studying the models and talking to the scientists, kind of, there's a point where you kind of get it at the gut level instead of just thinking about it. Things like climate change is basically irreversible. So all the damage that we're seeing now, you know, with all these extreme weather events around the world, that's not going to get better in the future. It will get worse, you know, the more that we put out greenhouse gases. And then when we reach this kind of net zero, we stabilize things, but the problem doesn't go away. We're still stuck with all of the climate change that's happened. So to me, and it took a long time to understand how the models tell us this and how we know for sure that this is true. But yeah, climate change is irreversible and hardly anybody seems to understand that because we're all waiting for somebody else to act upon it. That was surprising, frightening. I mean, the other flip side of that, the more hopeful piece of that, is discovering all the climate solutions that are out there. So I'm teaching this new course. It's called Confronting the Climate Crisis. And about week 4 in the course, I gave the students... Actually, people can go and look at this, whether you're taking the course or not. A wonderful project out there called Project Drawdown. It has a website and it lists like 100 different climate solutions. So I said for that week to my students, go and explore this website, pick 3 climate solutions and read up on them and bring them back to present to the rest of the class. Students were coming back to me saying, we'd heard all the doom and gloom in high school. We'd heard all about climate change. We thought we were doomed. We didn't know there were climate solutions. It's like nobody had talked to us about all of these things that we can put in place right now to address climate change. And so for me, that was eye-opening. That wasn't so much writing the book, but this was using what I'd learned in the book now in my teaching, taking students through a similar journey to what I'd gone through in finding my way into this field. It's surprising what people do not know about climate change that I feel they should know.
Yeah, I would say that was kind of eye-opening as well. And I guess it makes sense because everything that we see has been done over like centuries. So it's like we might prevent further damage, but if there is any benefit to be had, like, or any reversal to be had, it will happen well after our lifetimes.
Exactly. There will be future technologies, I'm sure, that will one day suck carbon dioxide out of the atmosphere again and perhaps undo that, but that's future generation stuff. Right now, our challenge over the next few decades is just to stop making it worse.
One last point I would bring up from the book, though, is that it was really nice of you, I guess, like to mention how with the solutions that we are sort of being given, it's all about individual contribution. But you do talk about that that's not going to add up sufficiently enough to negate everything else that's happening from big corporations or just bigger bodies.
Well, this is the whole systems change argument, that climate change is a fundamental problem of the systems in which we live, the economic system, you know, consumerism, the way things are manufactured and shipped around the world, the way our buildings are built, the way our transport systems work. There's all this infrastructure that locks us in to living our lives in particular ways that no matter how good you want to be as an environmentalist, no matter how green you want your life to be, the choices just aren't available to you. You can't. You know, our transport infrastructure, think about City of Toronto, our transport infrastructure is largely built around cars. And there are options, you know, there's the TTC. Still, you know, cars is the dominant mode of transport, certainly across North America. And that means if you want to do something differently as an individual, it's hard and you put a lot of effort into it, and probably you'll get frustrated and give up. And that's not how you solve climate change. It can't rely on individuals kind of voluntarily trying to do something that's a bit harder, fighting the system that they're living in. Now, you can't push that argument too far, because if you go too far, that says, well, then there's nothing we as individuals can do, so we'll just wait for somebody else to solve it. And that's not the right conclusion either. So what I try and do in the book, in that last chapter in the book, I try and say, you know what? The right way to think about this is not us as individuals, it's our communities. It's working with our communities. If you do things at the community level, then you really can make significant changes, and those changes will have a massive impact. So, if you do want to work on reducing your individual carbon footprint, that's great, but do it with a whole bunch of friends and kind of challenge each other, to push each other to go further and faster. And that's both easier to do because you've got a community all trying to do the same thing and discovering and sharing ideas, and it has much more impact than just one person trying to do it on their own. And then, of course, there's the political question, because really all of the solutions around climate change, all of the places where we need to make progress is in the politics. So we all have to be a lot more political than we currently are. We have to be engaged. And I don't just mean going out and voting every 4 years. I mean pressing our leaders to do the right thing in between elections, because that's where things really matter. So yeah, as well as working on your carbon footprints, go join political movements, get active, write to your MP, those kinds of things. That's another way that we have to work together to change things.
That's really great. So as we wrap up, is there anything else you want to add?
Having published the book last year and thinking about what I do next, and we speculated a little while ago about other books that I might write, but it's not obvious to me writing more books is the right thing to do either. One of the things that I've been thinking about a lot at the School of the Environment, in my role as director there, thinking about the courses we teach, is what's the role of a university in the climate crisis? Because I don't think our universities are doing enough. So maybe I'll just leave that as a question, but I think we've got to rethink what universities do, and I mean across the board, in what we teach and how we teach it, in what kinds of research we do, in how we engage local communities, how we engage with the world. Our universities are not where they need to be in terms of creating and sharing all the knowledge to really take climate action seriously. So it's a big question, but I think it's an important question.
Great way to end this off. Thank you so much, Steve. So that concludes our episode of Curious Campus with Professor Steve. If anything you heard today interests you, definitely look into his book, Computing the Climate. Stay tuned to Curious Campus.